Hi, welcome. Thanks for coming this morning for a 9 a.m. talk if you're here in person or whatever time it is in whatever time zone you're listening through on Zoom. So before we get going, I just want to mention that I've got a lot of stories over 5 years to tell, and so I have probably too much content that will fit in this hour. So there might be a story here and there where there's slides in the deck that I might just kind of briefly mention and skip over to save time, but the slides will be there as a reference, and you can ask me about that war story if we skip it in the hallway. And also, because I'm kind of going to cover kind of a few different areas of the story, from kind of some bugs and kind of technical details from undefined behavior to the kind of social and tooling changes we went through at our company. So instead of saving all the questions for the end, I'd like us to take questions as we go and have this be interactive. I also might ask for some audience participation. If you do have a question in person, if you can come to the mic, that would be great. If you shout off your seat, I'll try to remember to repeat your question, and let's get going. So let me just make sure my clicking situation is working right. So to tell you a little bit about myself and who you're talking to today, I'm Roth Michaels. I'm a principal software engineer at Isotope and Soundwide. For most of the era of these stories you'll hear, I was the technical lead for mixing and mastering software. And at the moment, I'm on the Soundwide audio research team developing new prototyping toolkits to have research prototypes in the hands of sound designers and PMs faster. I also want to give a thank you to my colleague Russell McClellan, who helped me prepare some of the material for this talk. And actually, when we talk about the tooling side of things, he did actually a lot of the heavy lifting, and I was more kind of one of the stakeholders in the feature requests. And he's also going to be giving a variation of this talk at the Audio Developers Conference in London in November, where he'll get into a little more details we won't cover today about other kind of weird situations we ran into porting to M1 with specifics dealing with being an audio plugin running in somebody else's audio editor. And if that sounds like a confusing sentence, I'll explain what I mean by that in a minute. So as I mentioned, I work at Soundwide, which is a merger of a few different audio companies. For most of this story, I was working at Isotope, so we'll hear, which is listed on the left, we'll hear kind of the perspective from that one company, but all of these companies listed here are making software for audio production, whether that's mixing and mastering albums or repairing audio for film and television or live performance. And all of these companies have a turn-of-the-century code base. So pre-C++ 11 code hanging out there, lots of weird stuff piling up over the years, except for SoundStacks at the end. They're new. You'll hear more about them in coming months. And to tell you a little bit about the context of most of the software we make are plugins that are DLL loaded in some other host program, whether that's an audio editor, like in the background here you see Logic, which is the audio editor from Apple, or or video editing software. And kind of one of the challenges here is you see kind of 3 different little plugins loaded, but there could be actually many copies of the same thing existing in one space, so we can't deal with any global state. And also this host application is in charge of all our threads and how they call us, and that's not always super documented. So there's a lot of interesting threading problems we sometimes have to deal with. So to start off, I had a question for a little audience participation. I wanted to ask about if anyone could mention thoughts about what they think the behavior of this function is, but don't answer yet. I just want to be clear. That's not how you make a random number. Did we ever see that for real? Come to my talk tomorrow about random number generators. This is not a real way to make a random number. So anyone have any thoughts about what the behavior of this function is? Yes? Actually close, but doesn't compile because it's missing a semicolon. This was a little bit of a joke. And the reason I brought this up, because I was making this talk, I remembered, I don't know if it was in the GCC plus LLVM days or when Apple switched to Clang, but all of a sudden I got this really nice warning about error. Oh, are you missing a semicolon here? Instead of this other really confusing thing about what the compiler thought many lines later when you're missing your semicolon. And so the reason I bring this up is that the tools are getting better all the time. And they're a lot better now than when they were giving us that semicolon warning. So it's great to think about and leverage those new tools. So the kind of correct answer is the behavior of this function is undefined. Anyone have any thoughts of what might actually happen if you run it?
You'll return the size of an unsigned bits worth of
That's one thing that can happen. Some people might also say it will reformat your hard drive. Maybe not exactly true, although I did have when I was first learning kind of my C chops in grad school, and all of a sudden writing audio code, pixels changed color on my screen. One of my colleagues asked, "Are you really like brave enough to like write undefined behavior in C on your like only computer? Won't you destroy everything?" And I thought, "Oh no, it'll be fine," and it was fine. I never erased my computer. Maybe it will make you sneeze. Chandler has a great talk about how the nasal demons and other hyperbole is maybe not the greatest way to think about undefined behavior. I recommend you check it out. But it is kind of good to be afraid of, and that's why he has it in big letters there. And as was just mentioned, this is an unoptimized version. It will just return some stack memory, like you said. But since this is undefined behavior, people often think, oh yeah, well you'll get an indeterminate value. Well, the value is indeterminate, but you can't read that. It's against the rules. So another option is the compiler can just do this. Just return and do nothing, erase all your code, because none of this is real. This can never happen. So has anyone written undefined behavior on purpose? All right, I see a couple hands shyly raising it. I'm proudly saying that early in my career, I don't remember what it was. Maybe it was some type punning thing. I read, oh yeah, this is undefined behavior. I wrote it, compiled it, looked at the code gen, and said, oh yeah, it does what I want. Good to go. But turns out that's not really the right approach to take, and we'll get a little bit more into that in a second. Can everyone read this? I think it's big enough. I'll just give you a moment to enjoy this cartoon if you've not seen it before. Yeah, so the punchline is, yeah, we're all bad at this and figuring out how to be software engineers, I guess. And related to this, there's a badge of honor my team brags about that we saw in a forum, people complaining about Isotope, and this guy, Dr. Driller, said, a longer post, but those guys are not serious programmers. And we take that with pride. They were complaining about a feature that we added many, many years ago that turned out to be inconvenient, and we actually saw this thread and removed it, but sadly couldn't tell them that it wasn't going to be removed for a few more months. And I bring all this up not to say that, oh, all my coworkers are bad, we're all bad at this, but this is actually challenging, and for a couple reasons. One, there's this phrase, C++, enough rope to shoot yourself in the foot. It's got a lot of rough edges. But also, it's not just like the rough edges today, but as I said, this is about legacy code bases, 20 years of code. There's a nice quote from Titus Winters that software engineering is programming over time. So a lot of the kind of strange things we'll talk about today weren't necessarily problems the second somebody wrote some code, but something somebody wrote 10 years ago, plus something maybe 3 years ago, and something now, wake a dragon and something scary happens. So to tell you a little bit about the agenda for today, we're going to talk a very brief, fast overview about what undefined behavior is, and some references to learn more about it. I'm going to show you kind of a couple interesting bugs and talk about the debugging experience to actually find these undefined behaviors and the strange stuff that was happening. And then we'll talk about culture changes and tooling changes we made at Isotope to basically stop the bleeding and not write any new undefined behavior and slowly make progress on purging it from our code base, which was really important when we no longer were in the world of everything's x86 and Apple comes out with Apple Silicon, and now we have new architectures with new quirks to support. So very briefly about what undefined behavior is, there's a couple kind of high-level ways that things are classified about C++ programs in the standard. There's ill-formed, that's a compiler error, you don't get a program. There's ill-formed, no diagnostic required, which it's an error, but the compiler doesn't have to tell you. And there's a nice quote in this talk from Chandler and Titus from a few years ago at CppCon about C++ is a language that has false positives for is this a program? That's a really interesting topic, but we're not going to talk about that compile time errors, but the stuff that can happen at runtime with undefined behavior. So C++, as far as the standard is concerned, is not something that runs on a Intel CPU or a M1 or whatever ARM chip you might have in your phone. But it runs on an abstract machine that describes certain behaviors, and then a vendor will make a compiler that will translate the behaviors of that machine into something that will run on your actual computer. So there's a few different kinds of behavior. Defined behavior, this is kind of what we consider deterministic behavior of this abstract machine, and these are the things that the standard says, if you do this, this is what happens. Implementation defined behavior, this is things, like size of int, long, is character signed, how pseudo-random number generation distributions work. Does your platform support something other than xtern C, like xtern Swift, which I know doesn't exist? Which that can also be dangerous for portability, but something to be mindful of, but not the topic of this talk. There's also unspecified behavior, which is things that are, maybe we can consider this non-deterministic behavior of the abstract machine. Even if your compiler generates something non-deterministic, from our viewpoint, the unspecified stuff, we just have to imagine that could happen anyway, anytime. And a good example of this is if you have a function that takes multiple arguments, and each argument is passed an expression, what order would those get evaluated in? Again, not something we're going to talk about today, but something to be mindful of. But the real exciting topic for today is undefined behavior. And this is the things the standard says don't happen. C++ programs don't do this. They make no guarantees what will happen. Compilers will assume this never happens. And as a result, if you do have a code path that makes an undefined behavior happen, anything could happen as a result. Now, probably no, it won't just issue a syscall to reformat your hard drive, but really ununderstandable things can happen. And we'll see through some examples that sometimes we might think that we can understand, oh yeah, here's what was going on with undefined behavior, like returning a int-sized thing from a register or the stack in our first example. But we'll see it's actually really hard to sometimes understand why things are going on the way they were when you have undefined behavior. And I would recommend, don't even try. Just don't write it, and kind of hopefully this talk will help you and your colleagues get to a point where you can have a, we don't write any undefined behavior, or we try really hard not to, but we're human, so we make mistakes. To get a lot more detail about this, there's a great talk, Back to Basics talk from a couple of years ago from Barbara and Ansel at CopperSpice, talking about undefined behavior. And they have a kind of a great quote in there that I liked, where they say that some people ask, like, well, can't we just list all the things and what would happen for undefined behavior? And that's like, oh, we got a technical problem? No problem. Cool. Basically, they use an example of a dictionary of words, and like asking about, like, well, what's everything that could have undefined behavior? They said it's like, well, what's the meaning of every sentence that has made up words in it? So that's a fun talk. I recommend you check it out. So I mentioned that there was a time where I wrote undefined behavior on purpose, and I thought I knew what I was doing. And at some point, my attitude changed. This is when I discovered an article. Not sure how I came across it, from Chris Latner, the LLVM blog, What Every C Programmer Should Know About Undefined Behavior. And he links to another article by John Rager about undefined behavior in C and C++. And this lit up a light bulb and corrected a mistake that young Roth had in his mind, that unspecified and undefined behavior are really different things, even though the English words might sound like, oh, unspecified, undefined, it means like, oh, yeah, something happens. But one is unspecified. This is a legal thing to happen in the language. We're just not telling you what will happen. Undefined behavior, from the C++ compiler's perspective, it never happens. And just to briefly mention something from John's blog. Oh, whoops, I did not mean to click that link. Sorry about that. Oh, man. I'm new to the clicker life, so sorry for getting a little carried. Oh, new tab. That's why the back button wasn't working. All right, I get it. Okay, 2 technical difficulties out of the way. Hopefully we won't have 3. So I will not be careful not to click that link. So in John's blog, he mentions 3 types of functions. And I think this is super useful to keep in mind for code review. Type 1 functions where all behaviors are defined, type 2 where some behaviors are defined, and type 3 where no matter how you call the function, it will always be undefined behavior. So a type 1 function is something like this safe divide where we're going to do integer division. And there's two situations where this function could lead to undefined behavior if we didn't have these checks in place. So you can't divide by 0, so we check if that's the case. And also, assuming it's 2's complement, if you take int min and divide by -1, that will give you int max plus 1, which would be a assigned integer overflow, so you can't do that. So we check both these cases, and we print some error and return 0. If it's all good, we actually do the division. So this works for all inputs. A type 2 would be one that, oh, wow, I'm sorry, that slide shouldn't be there. Floated around. That one was a scratch slide that should have gotten deleted. So a type 2 function is similar, but instead of actually at runtime safely handling those cases, we just have preconditions for asserts that, and we probably document in the contract, don't call it this way, don't call it this way, and if you didn't do that, you get a nice division. And type 3 are things like our example from the beginning. I'm just going to briefly look at a couple other examples of how this stuff gets optimized strangely. So this example of, let's say that we have a table of things and we want to, I'm really sorry, that slides got out of order, I believe. Anyway, this is the example I was trying to show you, is that we're searching through this table and you notice this bug where instead of doing less than size, it's less than equal size. So this is going to overflow the end of the buffer. So the only way this won't overflow is if we find what we're looking for before we get past the end. As a result, the compiler can say, oh, well, it's impossible to overflow the buffer because that's undefined behavior. So there's no way we're not going to find it before we get to the end. And this can get optimized just to be returned true, because it has to find it or else it would be invoking undefined behavior. Another common thing is an example of like disappearing null checks. We have this like is p, return p, if not, return 42. And all of a sudden, if you put this print statement in there, the compiler is going to realize, oh, well, you're dereferencing p. There's no way it'll be null. And it can just turn it into this. And this can actually happen at far distances in your code base. So it's not like this simple example. It's not so scary. But like if the compiler can see a mistake over here where you didn't null check, any null checks it sees after that can disappear. And there's a great blog post by Raymond Chen that talks about this example and shows how it can create time travel, some other neat stuff. There's also another talk from CppCon I recommend you check out if you want to see more of these kind of weird things that can happen with optimizations with undefined behavior. So that's kind of our little brief overview of kind of some of the things that the compiler might do when it assumes something can never happen. But let's get into some of the practical examples from my own kind of work experience. So in the abstract, I know some people ask me about this, about hearing about things that work on Intel. So this is some pre-C++ 11 code that still existed in our code base in some ancient bits. We weren't using it anymore. We can already tell it's got stuff we don't like. We've got a volatile, unsigned. It's probably being a little bit weird. And just a reference, a shout out for Herb Sutter has a great talk on the C++ memory model, and it's 3 hours long. So that's all the real details you want to hear about this topic and why what I'm about to show you is suspect. But I'll show you the implementations of this atomic read and atomic write. So we'll look at atomic write first on Windows. And seems to be doing something sensible. I mean, maybe those reinterpret casts, I'm not exactly sure, but interlock exchange on this volatile, like it's what the platform's telling us to do pre-C++ 11 for how to write this value atomically. And what does the atomic read look like? Oh, just return it. And we have some comment about how this is guaranteed to be atomic. If you watch Herb's talk, we see that that's not really the full story, and that's it's not just whether we tear the writes, but memory orderings. I really recommend you watch that talk if you want to think about atomics. And then the Mac implementation looks like this. There's no special system calls. It's just we write, we return. There was a big comment explaining about documentation and mailing lists. I'm not sure if this was Intel only or some of this related to PowerPC, but this was kind of some old stuff we had going on. And how did any of this work at all? I don't really want to spend a lot of time getting into that because I said this is a big topic, but the short version is compared to processors like ARM and Power, Intel has a very strong memory model. So when you load, that is actually as strong from loading from an int as a loading from an atomic int from what instructions get generated. But if you remember, C++ language doesn't know about that. So even though, yeah, maybe in assembly, it might be safe to just load and treat that as atomic, that's not what goes on at the C++ level. And this was a bit concerning to me when I first started, because I knew that, well, we're making these Intel assumptions here, but we've got stuff that we make that doesn't run on Intel. Like this device in the center is a portable recording device we made with running Linux on ARM compiled with GCC. We have iPhone apps, Android apps, and I was like, well, why are we making these Intel-only assumptions? Well, it turns out those Intel-only assumptions were ancient. They only existed in our Mac and Windows desktop code. There was no way we were ever going to use that on iOS and embedded. So we can let that slide, but we've got this kind of gross stuff in our code base. And honestly, in a big legacy code base, it can feel helpless when you know you've got like this UB from 10, 20 years ago that nobody that works here wrote. What are we going to do about this? And not that we have a code base as big as the Microsoft one that was talked about yesterday, but just this is a slide from another talk I gave recently. But if we were to look at the Isotope products that we consider P1 or the active development products, it's about 15 million lines of code. 13 million is open source. We're not going to really worry too much about trying to find all the undefined behavior there. If we encounter something, we'll certainly work with upstreamers. But over a million lines of shared code between our products, and it's really about 2 million lines of code that we've got 20 years of dragons waiting for us. So it can feel hopeless because there might be too much to fix. Also, people might have attitudes on your team like, well, we've been doing it this way. We've been reinterpret casting instead of copying for years. Why should we fix it or why should we change it? Well, it works. QA tested it. It does what we want. Like, isn't it fine? And some people might, as this is mentioned to me earlier in the conference, that some people on their team think that undefined behavior is something for intellectuals or language nerds, and it's not really about getting your normal work done. But that's not really true. It's core part of the language, or it's really a core not part of the language. It's all the things that are expected never to happen. And so it's, I think, important to understand and be mindful of. So before the kind of stories I'll tell you about the adventures we went through in improving our tooling and culture around this, I kind of want to mention where we were when we started when I joined Isotope. So we already were turning on all warnings that Xcode and Visual Studio gives us, except deprecation warnings. Those were not, and turning everything as errors except deprecation warnings. And there might have been a thing here or there from Visual Studio that we might have turned off a warning, but it's pretty much all warnings. Warnings as errors, both local devs and CI. We would run some static analysis and dream of static analysis from Clang in CI, but we knew we had a lot of errors and like it would just fail all our builds if we turned that on. So we weren't really sure what to do. And we were aware of the Clang static analyzers. Oh, I should say runtime analyzers. I'm sorry, typo. But they're not trivial to get running for us because if you're using like a UB sanitizer or an address memory sanitizer, and we're trying to test us loading in somebody else's audio editor, well, it's really hard to find one of those that's not going to trigger UBSAN or address sanitizer before they even get to your code. So we need to actually better test harnesses to run our code without having to deal with other vendors' undefined behavior. And this is something we've been clearly caring about for a long time. When researching this talk, my colleague Russell found this still open issue filed worked on by one of our original researchers and founding CTO to research address sanitizer. And you see Russell closed it 2,479 days after it was open, because when we found this, we realized, oh yeah, we're actually using this in CI now. So clearly the research was done. But at one point they researched it and clearly gave up and thought like, oh, this is too hard for us. And so that was the state where we started. And so I've got a few war stories to tell you about strange things that came up as whether we changed compilers, changed OS that we were building on, SDKs, OSs we're deploying on, and all of a sudden something crazy happened. So I've got a few of these quick stories to regale you of. So on the first project I was working on, RX, our post-production audio editor, one of our UX designers got a automatic, I don't know if it's automatic or not, but he updated Xcode through the App Store, and I think Xcode 8 was out at the time, and maybe went to that. We were still using, I believe, 7 or maybe 6, I forget the numbers. But he downloaded this new Xcode, and he showed us something really crazy was happening. So I couldn't actually reproduce this with the latest compilers, but I kind of simulated the bug. So, and this is our latest version, so things look a little bit different, but this is what the main UI might look like. And then this is what it looked like when the designer ran it with the new Xcode. You might see two funny things going on here. One is these radio buttons are now really long ellipses instead of round circles. And this tab is no longer a trapezoid, but has this weird triangle shape to it. It might be kind of hard to see on the screen. But basically, things are not drawing how they're supposed to. And we thought, oh, brand new version Xcode? Maybe we found a compiler bug. So Russell goes on IRC, asks for tips to figure out, like, did we trigger a compiler bug? They suggest this thing CReduce, which is a tool for, you write a test case, and then it kind of randomly changes or deletes lines of code until it produces a different output from your two compilers. And we made a test case, we put it through CReduce, and it ended up just removing all of our code and never like found an answer for us. And so we realized, oh, wait, maybe it's not a compiler bug. Maybe we have undefined behavior, because clearly it just decided all this code just didn't matter and relate to this. So now why we didn't, Russell and I, we knew about the Clang sanitizers. Why that wasn't our next move? Maybe it's because, like I said, we had some trouble bringing those up in like a full product. So our answer was a bit crazy, and around the office the joke was, you be the compiler. I had the production Xcode we were using on my computer. Russell had the new one. And we went into the draw filled circle function and went into disassembly. And Russell would read me every instruction from the new compiler. And I'd say, okay, 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 until we found one that wasn't the same. And it was really weird what was going on. So the moral is, we didn't find a compiler bug. If you think you found a compiler bug, most likely you have some undefined behavior, and it's you, not the compiler. And I say, okay, we did find one recently, a CodeGen bug with LTO and MSVC. It's fixed now. But over 5.5 years, it was always us, not the compiler. And we, this time, assumed it was us until we could make a test case that proved it was the compiler. And so to quickly show you what this bug was, this is kind of very simplified code, but we like draw a circle where we like make an ellipse out of an X and Y radius. We turn that ellipse into a stroke object. And then we use this stroke object to create a transform. And part of that is using this get transform. What this transform does is take a generic circle and do things like, well, we know that we're rendering it here within our parent, but that exists at this major position in the screen. So it's actually shifting it to the correct position on the screen. And perhaps that transform deals with like 1x, 2x, I forget. And it turns out that was our issue. It turns out we had a use after free there, because we were passing that to a third-party library that did something a bit strange. So this is what the constructor of transform looks like. It takes a reference to a vertex source, which it converts to a pointer to a vertex source, and it takes a const reference to a transform that it converts to a constant pointer to a transform. Well, that's a use after free, because in our example, get transform is returning a temporary. So as soon as we create this transform, the transform's dead, and now any use of that, when we call add path to actually add points to the rasterizer, we're in undefined behavior land. So the fix was to move it out of there. And the crazy thing is, when we were stepping through the instructions to see what was happening, for some reason, I don't remember if it was X or Y, but at one point, it's every function call for doing the transformations and adding the path or passing around X and Y coordinates in the first and second registers to the function calls. And all of a sudden, once we hit this use after free, the compiler generated code generator, instead of passing X and Y, it just passed X and X. And I can't offer any explanation why the compiler thought that was the right thing to do, other than it was in impossible territory. It's using this deleted transform object to do some work on X and Y. That's impossible, so what am I going to do with that? I don't know. I'll just pass some value in both registers and move on with my life, was my assumption. These days, Clang doesn't do that, but this is my point why don't even try to understand why this happened. We're in impossible territory. The rules of C++ reality no longer apply. So just briefly fast forwarding in time, before I talk about some other bugs, we started using static analysis a little more locally, as well as we also implemented some Clang automatic formatting checks for our code reviews and that enforced that by CI. And this will come back later with our tooling, but when we implement these format checks, we didn't want to make it so you had to reformat the whole code base and ruin all the Git blames. So we would only run Clang format in CI and compare, like, did you run the format hooks on change code. So we would only enforce the formatting rules on change code. And once we had that, we'll see later, that also helped us enforce other rules only on change code so we can make small things happen in time. I'll quickly go over a couple other war stories, but I want to save time, most of the time for the cultural stuff. Working on our mastering software, we had a crash that happened when a Windows update came around. And we ended up using, this time, we were a little bit smarter than just reading out assembly. We used the Visual Studio Static Analyzer to help us find the problem, and it highlighted this snapshot data struct. Anyone see something potentially dangerous here? It's this snapshot member, the color, is the only uninitialized part. And the reason for that was when we first made this struct, maybe 10 years ago or more, we would never use it without a color. We would make one and then give it a color. But a few things changed over the years. And to show you what this is kind of this part of our Ozone masking software in Match EQ. And you see there's these little analyzed audio spectrums here and here, the blue and the orange. And those are what we would assign those colors to. What changed was we made a change in how we wanted to save this data to disk. So previously, we would only save it if we actually learned this curve. But we now are saving it within all the kind of data of the whole plugin. And so there's a state like this where we have the orange curve on the left has data to save, and the curve on the right is still in its default constructed position. You think that's fine because we're not going to look at the color if we're not going to draw it. But something else happened when we also decided to change how we were saving it. Compression got involved. And this is not a real example of how the code worked. It was a simplification. But essentially, the new version of saving our state did two things. First, there's this lambda you see that computes size, where in the simplified world, it creates a snapshot data and compresses it and sees how big it is. Then somewhere else in the code, we use that size to allocate some memory to actually save the state. And then when it's time to do that, again, we create our default snapshot data, compress it again, and memcopy it, assuming the size is the same. But with that uninitialized variable, turns out that could actually change the bits, and the compression was different. It seems like for Mac and Windows for a long time, the first compression always yielded a bigger size than the second compression. All of a sudden, a Windows update a week before launch, that changed. And it was an exciting few days. And the fix is just add those braces and we're good to go. And just one very brief other thing. All of a sudden, non-determinism shows up in regression tests in CI, and code we didn't change. Maybe we changed compilers, maybe we changed SDKs, I forget the exact thing, but all of a sudden our Mac regression tests are failing, non-deterministically. So, all right, we're a lot smarter than before, we're not gonna read the assembly, it's time to use the sanitizer. So I fire up Xcode, I turn on address sanitizer and undefined behavior sanitizer, and I run our code through one of our DSP regression test harnesses. And essentially, I'll be brief about this. You can ask me, because I want to get to some more exciting topics, and you can ask me more about this later if you're curious. But essentially, we had this thing called a memory pool buffer that is basically like a vector, but uses a pre-allocated buffer for memory. Kind of like the std PMR stuff, but not as robustly implemented and predating that. And essentially what was going on is, imagine a situation where we create two of these. We have a buffer of floats to process that has a certain size. We say like, okay, give me temporary memory for that size amount of floats to do some analysis. And so we like run through an analysis function, and now we've populated that analysis buffer. And like, okay, now we got to do some high resolution calculations. So give me more temporary memory of the same size of doubles, and pass that through. And that all works fine. But where we ran into trouble, and you see the addresses kind of all line up, the alignment is all good. But where we ran into trouble is, it turns out this temporary memory just was giving you the net bytes available, regardless of alignment or whatever type you needed. And most of our code was always using multiples of 8s, whether it was bytes, whether it was floats, bools, or doubles. So it kind of everything was properly aligned. But in some cases, like if you're doing a Fourier analysis, you might not use the whole size, but the analysis might be n/2 + 1, which would then, if you look at the addresses now, our doubles are no longer aligned to multiples of 8. It's off by 4. And that was working for many, 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 many years without any detectable problems or non-determinism. And all of a sudden, it caused a problem. And how did this ever work? Well, Intel's instructions can do this, I think, but C++ says you can't. Maybe it was Apple's Accelerate library was making some assumptions about alignment that we didn't know about, that's Apple's SIMD and like BLAST library. But really, it's another example of it's not really worth understanding how we got into this situation. It just, it's outside the standard, properly align it, do what the rules say. So how do we make some cultural changes to start moving away and not add new undefined behavior to our code base? So some of it was a little bit of fear-mongering and trying to make people a little bit more scared about their failures or weird bugs. Another one was education, making sure not just the developers, but everyone, QA and other people in the company, actually understood what this weird stuff we're dealing with was. And we also made a rule. Don't write any new undefined behavior. That might sound a little silly, but it was actually a really important cultural change to have that be a written down rule. So fear the red builds. Previously, a build would be sometimes red and flaky. We think, oh, maybe it's something wrong with the build machine. It only happens on this one build machine. But actually, usually that wasn't the case. It was usually, again, it's not the compiler, probably not your build environment's under control. You might have some undefined behavior. So kind of whenever I'd see that people rerunning, I would just kind of scare them about nasal demons, etc. Another was sitting in with the QA and PMs when they were doing bug triage. It's something that might not be triage as high, but sounded really scary. I'd raise my hand and go, oh no, there's something really bad in our code base. We need to investigate, if not fix it. So for example, there was a bug where a genre classification in part of our AI mastering assistant was supposed to say like, oh, did it analyze rock? Did it analyze hip hop? Sometimes it would return an empty string. Sometimes it would return a string like that. Looks like we're probably reading some buffer that we're not supposed to be reading. And so this was filed as like a low or medium, but a few of us raised our hands and said, no, this is really scary. We got to fix this. And then another was actually teaching about this and also creating a more affectionate attitude about UB. So at some point when we started making these cultural changes, we're talking about, I think on a pull request or in Slack that, oh, I think we've discovered some UB here. And one of our QA engineers comes up to me, Jack, and says, hey, Roth, what's an UB? And so I explained to him about what undefined behavior is, and now we lovingly call these UBs when we find them in our code base. And it's not just developers. Sometimes QA, when something really strange is going on, they might come up and say, hey, Roth, I think we got an UB. Can you help me take a look at this? And the other was not just QA, but actually the whole company. So after that crash with the Windows update, with the uninitialized color, I gave a tech talk kind of for a general audience with a little bit of technical stuff on undefined behavior, but really trying to explain to the whole company that no, we're not like bad programmers, but we've got this very dangerous language, and if we're not careful, old sleeping dragons from code written 20 years ago, if we massage things just right, will create problems. And so that was, I think, a really big shift for not just engineering, but the whole company. And like I said, we made a rule. So we have PIZ1, which is a rule in our fork of the CPP core guidelines. Do not invoke undefined behavior. And we have about 3 paragraphs explaining why you should not do that. And this is probably motivated by PR debate when flagging undefined behavior, like reinterpret cast when you shouldn't mcopy, and people saying, oh, well, we did this all the time. What's the problem? Or QA said it worked. And the point is, even if we have undefined behavior, we don't want to make the situation in our code base worse. We want to reduce and this also helped us reduce cross-platform breaks for our Linux guys using GCC. And now that we have a rule as part of our guidelines, this is something now developers are more actively thinking about when they do code review. And so it's not just the intellectual language nerds, but everyone is now trying to watch out, are you writing functions that have undefined behavior in them? And we also made some tooling changes. So first of all, I mentioned our deprecation warnings were not warnings as errors. We were able to, in CI, turn deprecation warnings as errors in new code. And I'll show you in a minute that this allowed us to essentially, if there's a function discovered writing undefined behavior, we don't have to fix everything, but we can keep new code from ever using that function. We also started employing Clang tidy in CI, both for checks on new code and for some automatic refactorings. And we've also been starting to roll out address sanitizer and UB sanitizer in our CI builds. And we're engaging in manual use of thread sanitizer that I'll talk a little bit about as well. So this is a really cool thing. The deprecations that should be deprecation warnings as errors in new code. So we had this function, register parameter. So if you have some audio parameter like the volume or something, and you want to expose this to the external host we're running in, we would use this function and we'd pass it a pointer to t, which is maybe the float where we're storing the volume value. And then we'd pass it this value range that would say like, okay, it can be between 0 and 1 or whatever we decide the range was. Turns out there was a race in reading that and writing to that pointer that we would register as that parameter value that we discovered with Clang's thread sanitizer. And I keep mentioning Clang. I should say, I forgot to mention the introduction. I'm an Apple person from a long time, so most of my experiences with Clang, these sanitizers are also being added to Visual Studio. I'm not sure the GCC situation. I haven't used that in a long time, but when I say Clang, this is actually something that's happening to the industry, not just Clang. But anyway, so we had this function that had undefined behavior, and so we added deprecation warning, invokes UB, and we wrote a new function that now takes an atomic, and it has no race, and new code can use this function. And luckily, there was a lot of code that actually already abstracted this, so we could kind of fix this globally for code written over the past year or so. But we didn't have to immediately go back and change every place, which there's probably 2,000 to 5,000 of those places in our code base thinking about it and like actively develop projects. Because even that Ozone product has like 1,000 parameters or something. But now that that's deprecated, that will be, if anyone ever calls that function in new code, it will fail a build in CI, and then they'll see, oh, I'll go use the new function that's safe. We also employed Clang tidy in our CI builds for static analysis. So this is something you don't need to actually run the code. You can just get results without building and running a binary. It has many built-in checks. Some of them we don't like that don't fit our coding style, but we have a lot of the basic ones turned on. This can also be a method for running the Clang static analyzer. It's also not hard to write your own custom checks. So we have a few custom isotope static analysis checks we wrote ourselves. The cost of this is you will have to maintain your own fork of Clang and LLVM to do that analysis. We don't build with our fork, but we do use our own fork of Clang an LVM for doing that static analysis. And this has been a critical tool for preventing writing new UB, because a lot of these checks, are helping you avoid those things. We run it on every pull request, only on the change code to make sure there's no failures. And we also have the ability to write custom rules, which also allows us custom refactorings. There's a bunch of slides here to show you how we have this optional like type that had a implicit conversion operator. And it wasn't actually undefined behavior, because you see we would actually always initialize it and only work for default constructible types, but it was still a weird bug. If you expected something to have a value and you silently get 0 when it meant nothing, that can cause weird things to happen. So we were able to write and that we had this, operator equals that look like that, and the, that shouldn't have, that I don't think is, there we go. Here's the slide I was looking for. So we have our operator to convert to the T, and then we have this cast member function that also returns the value, but asserts if we haven't actually set a valid one. And so we were able to write a Clang refactoring tool that removed all cases of implicit conversions and switched them to this cast version, so we would at least get a debug assert if somebody was, trying to read a value that hadn't actually been set yet. So Clang tidy to the rescue, looking at a code like this, that if that checked value that's passed in was never set, we would silently get a 0 out of the count, which might not be what we wanted. Now we have this cast. If it's not set, we get an assert. I'm not going to go over it, but it's a little bit tricky writing these things, but just here's some example code of the actual Clang matchers we wrote to do that, if you want to reference that in your own time. But that's a kind of a pretty neat thing. It's something actually I hope I'd like to get better at myself, is learning how to write these to do automatic code refactorings, even when UB is not involved. The next thing we did was start using address sanitizer and UB sanitizer in our CI builds. So these are runtime checks for various forms of UB. You can look on the Clang documentation to list all the different checks and things that it does, but it would have found, it did find that third war story I told you about, and luckily static analysis could have found the second one, but all three would also have been flagged by these sanitizers. And our recommendation is build with the sanitizers enabled and run it for all projects' standard unit tests. And that will be like kind of the first small step you can take into getting coverage from ASAN and UBSAN. And then make a plan for rolling it out to your various projects, and also taking this one step at a time and eventually moving up the testing pyramid so you're not just running it on unit tests, but getting a coverage on more and more of your code base over time. And I just want to mention aside, you might need to set some environment variables to correctly load libraries to run with these sanitizers. I know this is the case on Mac OS. I'm not sure if this is the case on other platforms, but we'll get into that in a minute. So just to show you an example of something that the sanitizers can find, we had this, not worrying about, worry about too much what this does, but this essentially, we had a embedded data in our binary that's a bunch of resource files, and it has this table of contents. And this is kind of how we're parsing our funny table of contents structure. And it flagged these reinterpret casts as undefined behavior because it could be an alignment issue or other things. So the correct way to implement that is with memcopy. And this is something that was lying around in our codebase for a while. We never looked at that function in who knows how long. And the sanitizer found that error when we enabled the sanitizers on the unit tests in that library. And as I mentioned, you might need to actually load a dynamic library on macOS or other platforms to do this. So here's the environment variable, an example of loading the dynamic library for ASAN and UBSAN. It's a colon separated list of paths. Usually, but not always, if you run it on Mac, you'll actually get an error printed in the console like, hey, you didn't load this library, here's how you do it. And you notice I'm only listing UBSAN and ASAN here because you can't, as far as I'm aware, you can't use those and thread sanitizer. Thread sanitizer you have to use on its own. And like I said, you want to start with unit tests, but we're really now trying to think about, since we enabled this a year or so ago, actually I forget when, on our unit tests, how do we start getting this to the rest of our code base up to integration and end-to-end test level? So for us, this looks like we're running this on unit tests. Next thing we want to do is we have DSP algorithms that we do A/B regression tests on. That's the next place we want to roll this out. And then eventually, and an end-to-end test of the entire plugin. And here's where thread sanitizer might be more useful because unit tests are often single-threaded. And for us, that plugin format is VST3. It's one of the many audio formats. So, like I said, you don't have to fix this all at once, but as you make a plan and kind of over time get more and more and more coverage, you'll find more problems, and your code base will get a lot healthier. So this actually put us in a really good position. Because when I showed you that atomic read write, my concern was, well, someday Apple's not going to be on Intel forever. They're going to go with the wind and whatever is right for them. So Apple Silicon comes out, and we were actually feeling pretty confident that we were in a pretty good space because now we've not been writing any new undefined behavior. We're better with the tools about how to get to the bottom of it. And we decided before we qualified our products for supported on Apple Silicon and M1, we were going to take a tooling first approach before we even wasted the cost on any human QA resources. So for the thread sanitizer, like I said, this is another runtime sanitizer that can't be run with the others. We're not really using it on unit tests and running it by hand because most of our unit tests are single threaded. And so we decided we know we have these works on Intel dragons lurking with races and other stuff with threading. And so we're going to run thread sanitizer by hand, document all the bugs, and fix them before we even pass it off to the manual QA. Because we don't want them reporting, we don't want to chase ghosts when QA says, oh, this weird thing happened one time, and start trying to debug based on their repro. Let's just use the tools, find everything that's wrong with the threading that's not going to work on ARM, and just fix it. It found many threading bugs, like that register param one I showed you. But we say those QA cycles, we did waste a little bit of dev time and learned a lesson here. Turns out, at least at the time, I don't know if this has changed, thread sanitizer does not understand atomic thread fence. And we were using this library reader-writer queue from Moody Camel that relies for doing lock-free queues, and it relies on atomic thread fence. So the answer to that is you need to, in your thread sanitizer builds, annotate some global variable just make a global variable that is for no purpose other than annotating it with happens before, and you can use that global variable to kind of show your before relationships that was not being understood by thread sanitizer. I'm not going to get into the details of that, but there's two GitHub issues here. One to the issue that flagged this issue with reader-writer queue, an example that my colleague Russell wrote for how we address this internally. Ultimately, the author of the library fixed it in a different way, but I believe that library is fine now. But the moral of this story is the tooling actually made it pretty smooth process when we hand this off to manual QA, other than the undocumented bits of the plugin formats for the hosts, but that's for Russell's talk at the Audio Developer Conference. So we had actually a pretty nice time once we squashed all those thread sanitizer bugs. In the sake of time, I wasn't planning to actually tell this story. If you want to ask me in the hallway about the dangers of const casting, this is a legend from before a number of my coworkers worked there, but apparently we const cast something and we changed the meaning of silence within the whole host program. Even once you removed all of our plugins, silence was no longer silence anymore, and as we const casted a const pointer. So I can tell you that legend another time, because I do want to say, so there wasn't questions coming along during the way, so I want to save our last 6 minutes here for some questions. So thank you for letting me regale you with these hopefully slightly frightening, but also kind of fun stories. And are there any questions? We have an online question?
Yeah. So question from Josh Reed. What CI tool do you use to trigger deprecation warnings on new code without also triggering existing code?
Yeah, so something we wrote ourselves, but we first did this with Clang format and then as well as Clang tidy. you can pass to those tools what lines you want to run it on. So we use, and I don't think we use Git directly. I think we use, I forget the name of it, there's a Git Python library. And so we use that to compare the commit at the head of your branch to where it diverged from the main trunk of development and see, okay, what lines did you change on your branch? And then we pass those as flags to Clang tidy to say only run Clang tidy on these lines. The deprecation warning one is a little bit different because that's warning as errors. If you email me, I'll get back to you with a more real answer about that. I think that one we might do some funny stuff where we actually don't treat it as an error, but just look for the deprecation warnings and turn them into a CI error. But I realize I don't know exactly how that one works. So feel free to email me and I'll look at it and get you a real answer. Yes?
Hi. You described at the beginning how you wrote intentionally undefined behavior and then checked that it did what you wanted it to do and went on with your life. Did you ever encounter, when you tried to squash undefined behavior, code that wasn't easy to fix? I mean, all your examples were easy to fix once found, but did you ever encounter an undefined behavior that did something in the assembly that you didn't know how to reproduce without undefined behavior?
Luckily, no. I've heard some things. I don't want to name names of any companies, but I've heard about like core DNS or other internet infrastructure that's doing like memory map stuff and creating objects in one process and then materializing them without constructors in another process. And it kind of works. And also, if you were at the fireside chat last night, someone also brought up some issues of things that actually work in every compiler but are undefined behavior. Luckily, we did not have any of those issues. The trickiest one we came into was, I'm not sure if it wasn't that register parameter thing, but there was some other threading issue we ran into where switching it to using atomics was a performance loss on ARM. So we actually reached for the relaxed atomics versus the sequentially consistent atomics, which is really hard to code review and get right. So it was like, the fix was easy, but Russell and I spent a long time looking at that to make sure it was correct. And if you watch that talk I linked from Herb, that will show you kind of why you should really tread carefully if you think you can actually write that stuff and get it correct. But we did show it did have a significant performance impact on ARM.
Hello, thanks for the talk. One question that I sometimes had myself was, did you ever run in a situation where you think that some undefined behavior should actually be defined in some way, and it would make your life really much easier if the compiler would just handle it in a sane way instead of saying this is undefined behavior?
I mean, to some extent, that example I showed of the unaligned double access, it's a little bit frustrating sometimes when you think, especially when we were at the time, it's all Intel, and I know the instructions involved if I wrote the assembly, I could make this happen, and so that's maybe a little bit frustrating that that's the case. But I've come to the viewpoint that we should pretend the machines don't exist and just follow the rules, and it'll make your life a lot easier. I don't know if that answers the question.
Yeah, thanks.
We have another online question?
Yeah. Question from Philippe Gelman. Do you plan to replace the mem copy from slide 115 with standard bitcast?
Yes. I'm not. I think I'd have to look back at it. There's some situations where we're doing stuff where actually bitcast doesn't work, and unfortunately, you still need to use memcopy or replace it new. But actually, that's one of the things we also did to help encourage people to get out of this habit of not copy pasting, but using the same reinterpret cast tricks that they see all over the legacy code. Was we actually wrote our own bitcast based on the reference implementation because we're not on 20 yet. I think. Fingers crossed, we might do that switch in Q4, but yeah, so we actually wrote our own bitcast that we do use when appropriate. I'm not sure if that worked in that example or if it was just habit that it got fixed that way. But yeah, we have our own bitcast that we'll use. As soon as the header is available, we'll switch to the standard bitcast. And I think we're out of time, but we do have another question, I think.
Yeah, it's the last one. Question and a comment from Danny. Question is, how big are the teams and organizations you guys converted to using the new CI processes? And how was the cultural conversion journey overall? And the comment after that is, I'm very interested in your experiences with developers who didn't fear or care about tackling UB in general, but would rather rely on their own historical knowledge to avoid UB or tackle mysterious problems.
Yeah, so as far as the size of organization, that probably made it a little bit easier for us. So when I talk about like we made these changes at a company, I was talking with somebody at Microsoft earlier this week that was interested in this topic with like his own team. You might want to think about this as your team, maybe not the whole company, because for us, it was the engineering team for the desktop. Is really looking at just the desktop software when we're talking about this culture change primarily, although it did obviously impact and everyone's involved on the mobile and embedded side as well. But I think it's on the order, it's definitely order of magnitude, not 110. So it's like, we're talking like tens of developers and half that number of QA on these changes. Native Instruments is a much bigger company, and so I don't know all the details, but they've had similar stuff to go through, and they're at least 2 or 3 times our size in engineering. I don't know their exact engineering numbers. Brainworks, I don't know about their history, and it's a little smaller, but that is something that made it easier, is that we were, a close-knit group of people all living in the same room. When that like affectionate UB term came up, we were still, as a pre-pandemic, in an office together, co-located. We're now distributed. So that probably made it a little bit easier for us. But I would think about that if you're, on the order of 50 or hundreds of developers, you might want to think about making these changes locally in your team and then, bragging about the results to the rest of your colleagues. And thank you very much for coming. It was fun to share these stories.